The main focus of chapter 2 has been how to find the mathematical model.
I kind of like chapter 2. I had struggled with those electrical currents, and it was making sense now.
Simpler, right? How to find the mathematical model, which we call here transfer function. Okay? And this transfer function is generally this is, you can say, input output relationship. Okay. We have, in this context, we have looked at mechanical system, spring mass damper, and we have looked at electrical system. I'd like to assign you some self-study for this chapter, and this is actually going to be very important, and it will carry some credit. So we have looked at, see, when we looked at mechanical system, we looked at translational mechanical system. Okay? Since we are all aerospace engineers, rotational systems are even more relevant, especially when you're talking about space systems. So I want you to, I'll also assign assignments. As part of assignments, I'll give you 1 or 2 problems which you will know. Rotational systems, okay? So as part of your self-study, you're required to rotational mechanical system. Okay? And it's very simple. So if you compare force is equal to, not equal to, but you can equate it to torque. Right? If for a translation system, it's if you are applying force, for a rotational system you are applying torque. Okay. So this is the input. Displacement. So what you have studied is, you looked at linear displacement, right? This is the output. X of t. Remember. This is synonymous to angular displacement.
When you say synonymous, you mean the equivalent of?
Equivalent of angular displacement, which will be theta of t. That is what we use. Okay. And you have m is equal to j. You have m is mass, j is moment of inertia. When you're dealing with rotational system, moment of inertia becomes very important. You cannot just talk about mass. Okay? So what is moment of inertia? How do you define, how do you describe moment of inertia?
You said
Inertia?
I just had a question. You said moment of inertia is equal to what? What's that J stand for?
J is moment of inertia. So this is, if you're dealing with mass for mechanical translation system, right? When you're dealing with rotational systems, you'll have to with J, which is moment of inertia. What is moment of inertia, Raju? How do you describe moment of inertia? Moment of inertia is the distribution of mass about the axis of a physical system. So when you're considering mass, how do you consider mass? How do you take into account mass? You look at the center of gravity, and then you assume all the mass is concentrated at that center of gravity. What is center of gravity? Essentially, it is the center of mass. Okay. J. Why is J important? J is moment of inertia. For example, so if you're considering this cell phone, and this is your axis. Okay. So you have 1, 2, 3. Right. About which axis would you need more torque? You would need more torque this way, right? This and this, you would not need so much torque. Okay.
Which way would you not need more torque?
If you're moving this, right?
Mm-hmm.
You don't have. So, for example, your displacement is you want to move. This is the force.
Mm-hmm.
Okay. So, moment of inertia plays a role in the sense it is distribution of mass. How can you impact or how can you affect a rotational change by torque, right? What is the difference between torque and force?
Torque is moving, not moving, but
Rotational force.
it's
How do you apply torque? Can you apply a rotational motion itself? You cannot fundamentally you cannot apply a rotational motion, right? You always apply force about the center of, if the application of force is not passing through the center of gravity, it will result in a torque. Anything you push, anything you apply force, if it doesn't go through the center of gravity, it will result in torque. Got it?
Mm-hmm.
So for example, if you are trying to push a car, if you are pushing it laterally, what will happen? If you push it along the direction of its velocity, it will move forward. But if you try to push it laterally, that is perpendicular to the velocity direction, it will result in rotational motion. Okay? So that is important. This is your self-study assignment. Okay? The other thing we need to discuss, I'll just give you some. This will help you understand the whole. So we're not done with actually. Self-study. The other part of self-study is, yes, Rani, go ahead.
For the torque, what was that? If the force applied doesn't pass through it?
the center of gravity.
If it doesn't go to the center of, if the line of action, the force is a vector. If the line of action of the force is not to the center of gravity, it doesn't move, then it results in rotational motion. Right? Makes sense? When we talking about electrical circuits, we have discussed Kirchhoff's voltage law. This has been done. Okay. So Kirchhoff's current law you have to do a self-study. Now I'll just give this to you right away. If you want any extra credit on your exams, you have to learn this. How to apply Kirchhoff's current law. This This is not really extra credit. You may actually get this as a problem in the exam, but this will be extra credit. Okay. And of course, I'll help you out if you will. We can take once I give you an assignment, I'll give you how to. When we solve the assignment, we'll solve for this. Okay. The other very important aspect we discussed was, so this is your self-study. Okay? See, the scope of automatic controls is, as I've often told you, is limited to what we are learning. Let's call this the force system. Right? What we are learning, we are limiting that to LTI systems. Correct? But aerospace systems are
What did you say the LTI stood for again?
linear time invariant. See, aerospace systems are almost always non-linear systems. So does that mean that you cannot apply? In fact, if you think about any physical system, ideally speaking, there are no linear systems. Okay, all systems are non-linear. But aerospace systems in particular are actually, the models developed for aerospace systems are particularly non-linear models. So what does non-linear systems mean? How do you define this non-linear system or linear system? So this is, you have to go back to this input-output relationship. So if you're talking about, this will be your input, output. This would be a linear system. Okay. Non-linear again. Input. This is just an example. The non-linear.
And that goes back to those when we developed equations of motion.
Equations of motion. So any term, any system equation that has, let's say, a sine term, cosine term is a non-linear system. How does a sine or cosine term look like? You guys know that, right? So what does that mean? So if you input a value for the angle value is it what is the input and what is the output if you're looking at the sine circle? What is the input there?
When the input,
Hmm?
And
The angle is the input.
yeah, the output
Okay.
is what the sine angle would
The
be.
sine of the angle is the output. So here you'll have theta here, and the y-axis you'll have the sine of that angle. Okay. So that relationship is non-linear. Does that relationship look linear or non-linear? Non-linear. Exponential series. Is it non-linear or linear? Exponential series is non-linear, right? So all those systems are non-linear. So what do we do if you have a non-linear? You have a non-linear system, right? But you have to apply linear control to that.
so we take a difference.
You do linearization. Okay? So linearization, I'll just give you how to do linearization. And this is something you should definitely learn in MATLAB. It's a very simple way to, given a system, you can very easily linearize that system using MATLAB. Linearization, what is the linearization technique you've learned? Taylor series expansion. So what you're trying to do is have you tried to draw a circle in a computer? Can you draw a perfect circle in a computer?
Now it's in MATLAB or in
Huh?
MATLAB.
In any computer, any software programming.
Yes, they have tools now. You can just search it up.
No matter how advanced computers can be, it will never be a perfect circle. It will never be a circle, in fact. Okay? It will always be a polygon.
A what?
No matter how good your computer is, how advanced the computers become, as long as they are digital, you can never draw a perfect circle.
It's usually a bunch of squares if you really look.
Lines, it will be a bunch of lines. Because see, what is your computer screen made of?
Pixels.
Pixels, right?
Which one?
You have to always join those pixels. And you have to join those pixels by a straight line. You cannot join those. So no matter how advanced, so that is a very good example of linearization. So what you have done, you have linearized the circle. Right? You have made it into a polygon. So linearization, we'll just discuss a little bit of this.
So when you said the linearization in MATLAB, you're saying basically do the Taylor series in MATLAB.
Right.
It's very tedious.
So essentially your linearization, if you have for a function f of x So this is how you linearize. This is the Taylor series. If you have a function, will be given linearize it about a known point. That is what your listing will be. So you'll use this. It's very simple. So if you're linearizing it about some initial point, this will be given to you. Okay. You take the value of that function about that point. Then you take it. You differentiate it once. Evaluate it at that point again, and you take the difference divided by the factorial. So I'll give you an example. So a simple example would be how do you linearize f of x equal to phi cosine x about x is equal to phi by 2. So how do you do this? So you can say 5 cosine x is equal to
Well, we didn't
0
we
plus. So this is what? You have to just do this. This means x naught, okay? This is x naught. We have 5 cosine pi by 2 plus. So df over dx is what?
the sign.
Sine of 5 sine pi by 2. Okay. So I'm just substituting this as well. So what you do is, if you want to do that, then say do this x is equal to pi by 2. Okay. And then you have x minus pi by 2 divided by 1 factorial plus, what is this? That is minus. So actually this is minus, right?
Yeah. So then it's minus 5
So this
cosine.
is again minus 5 cosine x. Okay. Evaluated at x is equal to pi by 2. Then you have again x minus pi by 2 square divided by 2 factorial plus 2. Okay, so if you evaluate this goes to 0, right? So it's minus, what is minus 5, right? X minus pi over 2 minus 0. All the sign terms will have some value. It will be plus 5 x minus pi over 2 cube over 3 factorial plus. Okay. So this is how you go about linearization. So this term will be 0 again. This is the next term. Okay? This term is 0, right? Because cosine of, again, pi by 2 is 0. The next term will be 5 sine of x, again, at x equal to pi by 2. X minus pi over 2 cube divided by 3 factorial. So if you plot, so how would you compare these two functions?
Which two?
So you have 5 cosine x can be written as Phi cosine x can be written as this. This is the right hand side is the linearized form. Left hand side is the non-linear form. Okay. So if you plot this, if you substitute values for x,
It's x minus pi over 2 to the power 2n plus 1. 2n plus 1 over 2n plus 1 is factorial.
what are you saying?
Say it
So
was
what I mean is like the x value will be x minus pi over 2 to the power all the power.
No, x value can vary. You can vary x value from 0 to 360.
and that x on the
This is
left.
the linearization form. Linearized about pi by 2.
Oh, okay. You're just
So
asking
you just,
for the left side.
if you do an input output plot,
Is that x on the left the same as the x on the right though?
hmm?
That x.
Right. So this x and this x, right? So this is what, if you just use some radian values, right? 0 to pi, 0 to 2 pi. The cosine term will look something like 0. Something like this. The left hand side. Here x, this is the x value, this is the phi cosine x. The linearized form will look something like
Now why is 5 cosine x on the y-axis?
that's the output side. So input output. So this, it may not look like this exactly. It may look. It depends on how much you linearize, how many higher order terms you do. It may look. You see it? So I think this is better. So that's the reason I put this. So if you ignore the higher order terms is this series is an infinite series. It keep on going. If you ignore the higher order terms, if you just go by this, this is your x and this is the right hand side, the linearized form. You'll see something. Now, although you cannot apply this automatic controls to this, you can apply automatic controls to whatever you're learning. Is this a linear system? It's a linear system. So you can apply. You cannot apply automatic controls to this, but you can apply automatic controls to this. Although, if you're designing very accurate systems, you don't want to do this. Right? You don't want to just approximate it so. But you can develop very close to. So, for example, it could be something like this, It could be very closely linearized. As I said, this. Very small. It depends on how many higher order terms you include. The more powerful a computer system is, you can include much more higher order terms to calculate your linear. In computers, everything is linearized. Okay? You cannot solve a differential equation in a computer. You cannot seek a closed form solution you can seek a numerical solution, but you cannot, for example, this computer does it understand what is the differentiation of this cosine x? Unless it is told that the differentiation of cosine x is minus sine x. By itself, it will never understand. However, it will know how to linearize. You don't have to tell it because it's built that. So we'll just there's one more item. We'll just cover that and finish that.
Is x not negative 5 over 2?
Huh?
Is x not negative 5 over 2?
No, it's 5 over 2.
That's just a marker board.
That is just somehow.
Dr. Sunny,
Yes.
how do you get that first term on the last equation?
Huh?
How do you get the first term and the last expression?
First term,
And the last expression?
this one?
Yeah.
Huh? So you evaluate it at x equal to pi over 2. Right? So df over dx is 5 sin x. Sin x is what? How much? 1. Minus 5. This x minus pi over 2 remains as it is. Divided by 1 factorial is 1 factorial is 1. This goes to 0. So everything, this means evaluated at x equal to pi. That bar means evaluated at. You understand?
And the next, oh, never mind. That's the next one.
Why are we minus?
Huh?
Why is it minus 5 sin x?
The differentiation, what is the differentiation of 5 cosine x? What is df over dx of 5 cosine x? It's minus sin x, right? So some of you will have difficulties with electrical systems. So what you should, you can explore this. I have already given you some leads, some hints about similarities between electrical and fluid flow, right? Think about this again. But the other way of looking at this is, just look at this and finish off. Just give me a couple of minutes. If you have a system like this, and this is what you really need to appreciate here, okay? This is a mechanical system.
What's the symbol underneath what I want to call the pusher or whatever? The symbol, it looks like TV from here, but what is that?
This one,
No, above in the first drawing.
f of b.
Oh God.
Okay. So these two, you can say electromechanical equivalence. Okay. What it means is, you develop a transfer function which is the input output relationship for this. You develop a transfer function which is the input output relationship for this. They will look exactly the same. Mathematically, they'll look exactly the same. You understand?
Which two will look the same?
So this is a mechanical system, this is an electrical system. And once you have developed that mathematics, they will look the same. And when you seek a solution, this is the power of mathematics. When you seek a solution, you don't know what system are you seeking a solution for. You're seeking purely a mathematical based solution. Right? So here, so mass m is equal to is compared to the inductor. Okay. The damper viscous damper, which is Fv is compared to resistance. Okay. Fv
Is there any Henry's?
Henry's, yes. Spring, which is K, is compared to capacity. So it will be 1 over K. And apply force which is F of T is compared to voltage source. And finally, so we have always been dealing with displacement. Until now we have talked about displacement, right? But you can always, so here V of T, what is V of T? V of T is not voltage. Here V of T would be what?
Current.
In this system.
Oh, displacement.
What is it? V of T would be what?
Velocity.
Velocity.
Mm.
Your output can be displacement or it could be velocity as well. It depends on what you are seeking out of the system. What do you want to measure? You're not always interested in measuring the displacement. For example, if you're talking about driving the car, are you really interested in measuring the displacement? You're more interested in continuously you want to measure the velocity, right? So this V of T is the velocity.
In the spring capacitor line, the unit is 1 over K what? That's 1 over K what?
Farads.
Farads.
That's the unit. So we use F and capital H. Remember? So this is the, it becomes current. So if you just look at this one, transfer function, okay? The transfer function, you have ms square plus ds plus k divided by s. Surface is equal to ms plus fv. So this one is mechanical system. Okay. This is electrical system.
Now that F, V, is the S like in the exponent or is the S side by side? You hear me? Is that for the mechanical system? Is that FV to the power of S or is
Now
that
FV is just this FV into S
so S is in the corner?
multiplied.
Oh, S is so it's FV times S.
FV is just a symbol.
Okay. Because they don't look side by side, but I understand.
Okay. S is the frequency variable. So you see this. So you have to compare. This is the mechanical system, and this is the electrical system. And try to look at this. Why is this X S into X of S? Alex, transfer function This is a transfer function, right? So what is transfer function? If we go back to the definition, huh? Output over input. Okay. What is the output here? We are seeking here. What did we say is the output?
Velocity.
Velocity. So velocity is d over dt of displacement. And what is the transfer function of that? S into x of s. Because it's got it? Velocity, if you, v is what? V of t is d over dt of x of t, right? If you take the Laplace, it is v of s equal to s into x of t. So you see this x of s. Okay. So this is chapter 2. Starting next class, we'll do chapter 3, and you'll get an assignment today for chapter 2.